Okay, so Peter East, he's going to give a talk on adapting PRESTO pulsar validation techniques for amateurs. Says, living just 20 miles south of London, Peter is a retired engineer after a fun career in radar and electronic warfare systems design. He has made several contributions in the SARA Journal and is a long-term member of the British Astronomical Association and a member of SARA since 2013. He's also had an interest in radio astronomy and still enjoying the challenge of pulsar detection using small instruments. Okay, Peter, go ahead.
So the talk is adapting PRESTO pulsar validation techniques for amateurs. If you're not into pulsars and wondering what this is all about, the question I'm expected to answer is, I'm changing around. How can a pulsar hunting amateur be sure he has a valid intercept? He may have proven his system sensitivity, he's built his radio telescope, checked that the pulsar is within his antenna beam, checked the recording is not blanked by RFI, radio frequency interference, and suitably integrated their data, and produced a record that looks like a pulsar, maybe something like this. Now, the question we've got to answer is the spike in the middle a pulsar, or is it a noise pulse? Is it an RFI pulse? Or is this the pulsar? And why have I chosen PRESTO? Well, there's a trend amongst the amateur pulsars hunters to use professional pulsar software, PRESTO, for pulsar analysis and also to confirm validation. In this talk, I'm going to introduce PRESTO, say how best to use it for pulsar analysis, the limitations it has for amateurs is not perfect, and how to adapt the PRESTO processes to better get the information that you would like. Okay, and then end up with some results. Right, PRESTO is a large Linux suite of software, pulsar search and analysis software. It was developed primarily by Scott Ransom. We started it almost 20 years ago. To date, it's detected over 1,000 pulsars. PRESTO stands for Pulsar Exploration and Search Toolkit. For data collection, most amateurs nowadays use GNU Radio plus an SDR. There are two really good software packages available, one written by Marcus Leach and the other one written by Andrea and Giorgio Dell'Immagine. Both produce standard PRESTO compatible filter bank files. If you look at the PRESTO instructions, then you can see the word search, and this is primarily what it was intended for. You collect an awful lot of data, and I believe it was used for the Arecibo dish, and they collect the data and it's processed, and the job really is to search for new pulsars. Now, searching for new pulsars is probably an aim for an amateur, but it's unlikely. He's unlikely to detect any new pulsars with all the work that the professionals are doing these days. But if you look at the instructions, there are two main items in there that amateurs can use. The first one is a tool called RFI Find, and that searches your data for RFI and with your help removes the worst parts of it. And number 12 is prepfold, which we use to fold the data to recover in the best way the pulsar's pulse. Some of the more serious amateurs can use prep data and some of the spectrum analysis techniques, but you really do need big, strong pulses for this. So the two packages I'm going to describe, the first one is for RFI mitigation, and it's RFI find. It's a command line instruction. The output is a mask file. The time is the sort of time period in blocks that it works on. Frequencies, freq-sig and time sig, they set thresholds for spectral RFI and transient RFI. There are lots of commands for this, but two other command line useful ones are zapjan, which enables you to blank certain frequency channels, and zapints, which allows you to blank some blocks in time. So if you get any serious interference over a short period, RFI find allows you to find those, and you can blank those out. The next one is prepfold, which is the folding technique for folding analysis, and it takes the mask that you've produced for RFI find. You tell it the number of frequency channels in the data. This is the number of bins in your fold. Minus P is the topocentric pulsar period, and that you obtain from another package called tempo, which you input your latitude and longitude and UTC, and it tells you the precise period that you expect to see, and this accounts for the motion of the Earth around the Sun and the solar system relative to the target. DM allows you to input the dispersion measure for the pulsar that you're interested in, and PD allows you to adjust the period rate in the search, and this is looking for any change in period during your observation time. And we know that pulsars are very, very stable, so there should be very little change in time, but this term allows you to find it. You call up no search. If you don't call up no search, then it will search over a tremendous range of periods, dispersion measures and period dots, and it will find probably some of your best RFI. Find tells you to do it. Find and file now fill is your filter bank program produced by the GNU Radio software. Just to remind you of what the folding algorithm is all about, in case you're not all familiar with it. Basically, the folding algorithm takes your data record, this is the time that you've taken it, and chops it up into blocks in time exactly equal to the topocentric period that you put in prepfold. And if it does this, if a pulsar is present, it will appear in the same relative position in every period, so that when you cut these up digitally and stack them one on the other, the pulsar, if it's present, adds linearly, the noise adds as the square root, adds as power, adds as the square root, and so the signal to noise ratio improves as the square root of the number of periods. This is an example of a PRESTO output, and it's a pulsar with a signal to noise ratio of about 35 to 1. This here is the best pulse profile, and it's repeated twice to account so that you can still see it if it appears at either at the beginning or the end, because it can appear at any position in the plot in the period, sorry. And this plot below is a time waterfall, and it actually goes upwards. And so this is time 0, and this is the extent of your observation. And it's broken up into, in this case, into 64 sections, and each of those time sections are folded and plotted horizontally, so that what you're seeing down here is the vestiges of the pulsar. They're just about appearing. With 64 sections, the apparent signal-to-noise ratio is reduced by the square root of 64, which is 8. So we're seeing effectively in each one of these blocks a signal-to-noise ratio that averages 35 divided by 8, which is just over 4 to 1. And so it's just peaking above the noise level. On the right-hand side of this, we see another plot which is labelled reduced chi-squared. Now, this is a power statistic that's used very heavily in Presto, and I'll explain it a bit more later. But actually what it's doing is it's integrating the power over this waterfall, and what you expect to see is a rising curve here. This central one is a frequency waterfall, and in this case there are 4 bands, 1, 2, 3, 4, and you can see that with the signal-to-noise ratio isn't significantly reduced, but you can see that it is in every, the pulsar appears in every band. This bottom one is the dispersion measure plot, and once again we use the reduced chi-squared to sense it, and what it does is it scans all the dispersion measure values, and what we expect to see it to peak up at the pulsar's dispersion measure. Now this is pulsar 1642, and its dispersion measure is about 36. So you can see this is peaking up at about the right place. On the right hand side, we've got 3 plots here. The central one is the a period search, and in this 0 represents the matched period, and then we change the period in small parts per million, positively and negative, and what we expect to see is a peak at 0, and we expect it to run away. When the period doesn't match the pulsar, it doesn't integrate. And similarly, this is the period P dot, it's called period rate, and once again we expect it to be a very stable source, so we expect to see a peak at 0, and as we change the rate away from this, then it drops off. This bottom one is a 2-dimensional plot of period search horizontally and period rate search on the y-axis. And what we expect to see here is a peak in the center corresponding to these 2 peaks. And we get this interesting significant signal at an angle here, and I'll talk about that later. So this is a good pass for the prepfold software. And if we look to see what it means that the profile tells us we've got a pulsar that matches the correct pulse width. The time waterfall tells us that it is a pulse train. It's appearing in every section, and we can see the evidence of scintillation where it goes bright and dark. The frequency waterfall tells us that it's a wideband source. The dispersion measure plot tells us that it's extraterrestrial and it's an interstellar source. And the period search confirms the accurate match period. The P-dot search confirms that it's a highly stable pulse train with negligible frequency drift. And the period P-dot plot tells us that it's a high stability pulse train and there are no ambiguities. The second one is a similar plot, but now I'm looking at a 15:1 signal to noise ratio. So we see that there isn't such a great signal here. If you squint your eyes, you might just about manage to see some traces corresponding to these pulse positions. But the reduced chi-squared, there's a jump at the beginning, which I can't explain, but the power is still going up as we integrate these periods. So that tells us that the signal is in everyone and it's getting stronger. The frequency waterfall now has 25 subbands. It's been driven into 25 subbands. And I think you may just about able to manage to see a couple of traces here confirming that that is a wideband source. The dispersion measure now shows us a peak. There's not so much amplitude discrimination, but there's a clear peak there, and it's peaking up in this case around about 30, which is around about the dispersion measure of this pulsar, which is B0329. The period search plot and the P-dot search plot are looking a bit noisy, but they're still peaking up at 0. The two-dimensional plot of period against period P-dot is showing us we do have a peak in the center and there is this stretch. So we'd probably call that a pass. The next one is a 5:1 signal to noise ratio, and whilst we can see the pulses there, there's nothing there. The reduced chi-squared is jumping at the beginning, but it's in fact going down rather than up. We can't see anything here. We can't see anything there. There's no firm peak. Nothing here, nothing there, and this looks pretty ambiguous. So that would be a fail. Now the point of this is to see why it's failing, because it does look like a pulse. And the reason is what I've plotted here is the integrated true signal to noise ratio, the sort of ratio that we do see. And if we look at the chi-square plot, which is this blue one, there's a nice differential up at 30. There's a reasonable differential at 15, which is what we've seen, but round at 5, there's hardly anything. And so basically this chi-squared power sensor isn't really given us much hope at this bottom level. If we look at peak signal to noise ratio, we expect, if we measure the peak signal to noise ratio at low levels, the normal peaks of noise is round about 2.5 to 3:1. So it's a bit flat at the bottom. But when it gets above this, the observed signal to noise ratio should match the input signal to noise ratio. The chi-squared statistic is duty cycle sensitive. So for higher duty cycle signals, say 3:1, 3% duty cycle, then it gives an improved differential here. Right, here's a couple of equations. This is the chi-squared equation. Looks very complicated, but actually it's very simple to implement because it's just the sum of squares. The signal to noise ratio, however, is a lot more complicated because you have to identify the peak. You have to strip it out from the noise so that you can measure the mean and the standard deviation outside the noise, and takes a lot more time. And if we look at the effect of this with the chi-squared and a 5:1 signal to noise ratio, it's all noise at the bottom here, and we get our signal at there, and we're seeing a sort of ratio of 1 to 1.16, whereas signal to noise ratio gives us almost a 2 to 1 range here. The reason that Presto uses the chi-squared is that it's very fast to implement, and in the search mode, you search a lot of periods and a lot of dispersion measures, and so the time taken is significant, and so that's why a chi-squared has been selected. But we can see that there are advantages in using signal to noise ratio. Now, the prepfold plot doesn't actually tell us signal to noise ratio, but it does produce a best profile file. And Giorgio Dell'Immagine and Andrea Dell'Immagine from Italy have written a Python program that will pluck the data out of the best profile file and plot the signal to noise ratio. And here we can see we have a signal to noise ratio of nearly 6 to 1, but it'll also tell you the position, where the peak position is. So if we use prepfold, we can adjust the dispersion measure. I'm looking at the dispersion measure now. We can adjust the dispersion measure and get a value of the signal to noise ratio for that particular value. And if we do that, it's a bit laborious, but you'll get all these red points of plotting the signal to noise ratio as a function of dispersion measure value. And here you can see there is a rough peak round about 27 where we expect it to be. There's a bit of an offset here, and I think that's due to the time increment of the data being 1 millisecond. The blue curve is a theoretical curve. If you look at our data and split it up into our periods, when the pulsar is correctly de-dispersed, you get the largest pulse, and when we add them up, we get the peak. But if you disperse it at a different figure, then it starts off as being broader, and it's lower in amplitude. And you can actually calculate what the amplitude will be and what the effective width will be, because as it gets broader, the pulse gets broader. And this is a plot of bid number. And so as well as the amplitude changing in a predictable way, the peak position changes in a predictable way. And so this is another measure that you can use to ensure that you really are looking at dispersion measure. Period is much the same. You can adjust the period. In this case, I've changed it in half parts per million, 0.5 parts per million. And once again, this is the peak signal to noise we're seeing here. And we're seeing a peak at 0 where we expect. And once again, I've plotted the theoretical curve, and you can see there's a pretty good match to it. I'll jump on. For period, in this case, I've shortened each period, And so gradually the pulse appears to shift to the right relative to each block. And once again, when you sum them up, the pulse gets stretched and the amplitude increases, and the bin position changes as well. And once again, this is where we've calculated where the previous calculated plot came from. And the same thing happens with period rate. You change this in parts per 10 to the 10 seconds per second. And once again, you can use prepfold and the signal to noise ratio plot to get these points. And then you can check them with this theoretical plot. In this case, it's a lot more complicated because the periods are changed. So that's changed in 1 p dot period, 2 bit p dot, 3 p dots, and 4 p dots. And so these tend to relatively go out faster, and so you don't get so much integration towards the end, and the peaks stay much closer together. So that accounts for the sharper peak that we saw there. Now, if we look at those results, we've got the profile, we've got that from our signal to noise ratio plot. We've done the dispersion measure, the period search, and the p dot search. So we know it's an extraterrestrial source. We know it's got an accurate match period, and there's negligible spin down. But we haven't done the time waterfall and the frequency waterfall, but we can do these within prepfold. But then the work gets much, much harder, because what you can use is RFind to block off parts of the data so that you can, in this case, I've sectioned it into 4 parts, 1, 2, 3, 4. And so you have to generate a new mask file for each of those sections and then do the run again. So I've diverted now to using MathCad and using I'm copying the processes that Presto uses. And so I've broken it into 4 parts here, and you can see here the pulse is appearing in all parts. It's a bit weaker here and a bit weaker there. But you can see that it's now coming in to the noise peaks are popping up, but they're not integrating over the whole length. And I've also done a peak signal to noise ratio, so it's growing from, that's just one period, one section, up to all 4 sections. And you can do the same thing with frequency by zapping channels, blocking it. Here I've selected just the central channel, which is this one here. And you can see once again, because it's only a 5:1 signal to noise ratio, at least we're seeing components in all parts here. They're at different amplitudes, which is an indicator of scintillation, which occurs for in both time and frequency. This is the most difficult plot to repeat. It's the 2-dimensional period search, p dot search, and here you can see that there is a peak at the center. It's a bit off center here. And we have a slope. And when you do the calculations for this, you find that the slope should be -2 divided by n, where n is the number of periods in your data sample. So it's a pretty good check that this is a continuous pulse train. The thing you notice about this is it is much extended along this line. If we look at 0 p dot, there's only a narrow range, and if we look at 0 period search, it's only narrow, but along that line it's much larger. Sorry, I'll move back. It's much more extensive, and the reason for this I'm explaining with this plot here. If you imagine that this is our n periods of data, if our period increment is 0, we pick up all of these and we get our maximum signal. As we move our period away, the amplitude goes down, but we can choose a p dot so that it brings it back down into this matched range. So here we're illuminating the center, and there's very little p error now, because the p dot setting has reduced this down, and in fact the slope for that gives us our -2/n. And this occurs at all levels. So if we have a very large period offset, we can always find a PD that goes through the center, and basically what's happening is this ellipse just gets smaller and smaller, and that accounts for that winding down of this. And if you look at the data closely, you can see it going out with this sort of coarse plot. It's not easy to see, but it does stretch over quite a large range. So this is quite a good indicator of a continuous pulse train. And none of these processes seem to mind scintillation. I said that the calculation is a bit complicated. Well, this is the fold calculation for period search and p dot search. And what I'm showing here is the green dot is for a normal fold with no period error and no p dot error. The magenta is what you get with a positive period offset. I explained the amplitude goes down and the pulse gets broader. The negative p dot is in red here, and you can see that is once again is spread right out. The pulse gets wider, but the peak is closer. And the blue is in fact both of them together. It's not intuitive, but if you look at these two, and that's why I explained those two. But this is what's happening. The p dot is pulling the period back into that central part. On the time waterfall, when I looked at this signal to noise ratio increasing with time, it seemed it would be better if, instead of plotting the section folds, I plotted the integrated section folds. So at the bottom we have just one section. By halfway we're folding all of that half, and by the whole way we're folding the whole lot. And in this way you can see the pulsar peak creeping out of the noise and getting up to its full amplitude at the end. Halfway, it's only about halfway. And here you can see evidence of scintillation. One of the most interesting things I found of this plot was that the noise peaks seem to be pretty consistent. I didn't expect them. I expected them to stay random, as we are here. But the reason for this is that the folding algorithm is in fact a very finely tuned harmonic filter. And what it's doing is it's filtering out the components in the noise that match the period that we're choosing. So it's seeing them as lots of little pulsars. But the difference is that they don't tend to integrate. They just stay around about the same sort of level. Some pop up now and again, but then go down again. But I've looked at several lots of data and they all go like this. So now let's look at the other thing I found interesting was these cumulative statistics. I'm looking at the peak signal to noise ratio now, and I'm now looking over 100 sections. So I've split the data up into 100 sections, and I'm looking at the cumulative signal to noise, peak signal to noise ratio. So it's starting off around about 3 to 1, and then gradually creeping up to 5 to 1. By the time it gets here, you can find out what the largest pulse is. And so you can use you find the maximum bin, and you can plot how the signal to noise ratio increases on that. And you'll notice that the pulsar kind of takes over around about halfway with this 5 to 1 data. For interest's sake, I plotted the chi-square. And you can see that it starts off at 1, which it's supposed to do. Another way of looking at the chi-square is that it's looking for a Gaussian noise distribution. And it's the ratio, and if it's a Gaussian signal distribution, it will come out at 1. But as the signal rises and the power increases, it should rise away from 1. The next thing we can do is to plot, as I've done here in blue, the section signal to noise ratios. The black line is the signal to noise ratio, the average signal to noise ratio we expect with a finishing 5 to 1. And we've got 100 sections, so the average signal to noise ratio is be 5 divided by the square root of 100, which is 0.5. So we should see an average of about 0.5, which we're seeing here. Now this cumulative curve will only rise if the section signal to noise ratios lie above this line. If they lie below the line, then it starts to fall. There's a section here where it's below the line and it's falling. Now we can probably, this is due to scintillation, and because we've written the program, we can cut out those bad sections, and if we do that and then integrate, we find that we can improve the signal to noise ratio from here, in this case from 5 to 1 to about 6.5 to 1. I probably hear somebody saying, you're manipulating the data. But is this any different from RFI mitigation? I don't think so. Okay, we put all that together so that I've copied the prepfold plots now. And here you can see the best profile. Here we've got the falling, the time waterfall, the frequency waterfall, the dispersion measure peaking at the right level, the period search peaking at the right level, and matching very closely the measured data, and the p-dot doing exactly the same. And this is a different set of data than I used with prepfold, but it is showing the same effect. So is that a pass? Well, for a small signal to noise ratio, I think I've shown that it's best to use the peak signal to noise. What I've shown with this MathCad plot, incidentally, all the software for that will be in a paper I'm hoping to publish in the journal, in the August journal. The profile gives us pulse width, time waterfall, scintillating pulse train, frequency waterfall, wideband source, So all of these are identical to what prepfold produces. And then I ask, is this enough? And I've probably just about got enough time to finish this off. If we look at our complete folded data, to produce this, I recorded about over 100 gigabytes of data, and the folding algorithm has reduced it down into just 714 points. Now, there isn't I haven't found an algorithm, I don't think anybody else has, that better will give it a better signal to noise ratio than the folding algorithm. But in doing that data reduction, we're losing a lot of information. And we can see this because if we split the data in half and fold each half and then overlap those, we see that the pulsar still appears where we expect it to, but the noise is now decorrelated. Now, I found an identity, which I won't have time to go into, but if I apply that to this data, the negative noise gives us no information. It's the pulsar, if it's present, will only be positive. So if I just take the positive parts of this and multiply them, if I take the negative parts, I get some funny numbers. But if I do that, the square root of a and b, twice that is equal to a plus b. And what that means is that the pulsar will always come up at roughly the same size as the original data. But the noise, if it's 0 or it's small, it will cut out. We're seeing some of the noise bits cut out. So there are a number of techniques you can do. You can randomize the data and then split it in half. Randomize the data, split it in half, you'll get different noises. You can carry on combining those, and gradually I've seen these all reduce. But in this particular bit of data, I thought I'd try an 8-section fold. So I split the data into 8 sections, and they're all overlapped. The pulsar should still be in the center, and I've expanded that here, and you can see that the signal to noise ratio varies in the parts due to scintillation, and it goes from about 0.8 to 1 to about 2.8 to 1. And if I apply that algorithm to apply the 8 version of the algorithm to this, you can see it's rejected all the noise completely, and it's just highlighted the pulsar. Oops. So in conclusion, for professionals and big dish amateurs, we know that Presto is optimized for finding new pulsars fast. It's great for RF mitigation, and Presto analysis is fine for signal to noise ratios, and where P is the pulse width, the P is the period and W is the pulse width. And in this case, it comes out at about 12 to 1 for B0329. And Presto confidence checks have been well proven. But for all amateurs and with low signal to noise ratio targets, even big dishes can have low signal to noise ratio targets. To mimic the Presto processes with peak signal to noise ratio, replacing chi-squared, the Presto confidence checks are fine for all pulsar characteristics, and the noise decorrelation technique I've shown you is a confidence booster. Thank you very much.
Hey, great, Peter. Got one question from Wolfgang. Have you tried RFI clean instead of RFI find on low SNR observation data to see whether it is performing better?
Well, actually, Wolfgang, I've been very fortunate. I've done most of my measurements at night to avoid RFI, and I've only found I have to do a minimal amount of cleaning. And in the data I've shown you, there's been no RFI mitigation at all. That was the data as I recorded it. But no, I haven't tried clean. And I haven't got to the bottom of all what is possible with Presto either.
Yeah, that's a lot of us. And okay, any other questions for Peter? All right, great. Any of you guys, there's a bunch of us that are doing pulsars right now. So if anybody wants to jump on the pulsar regime, I think Peter and Wolfgang and myself have done pulsars, and we'll help you get there. Just go to the listserv and ask. Let's see. Whit says, "A nice presentation, Peter. I also saw your pulsar presentation on the RAG Zoom meeting, and I'm slowly learning about them."
Good.
All right.
Thank you.
Okay. Well, thank you, Peter.